Okay, people. Grossly mistaken. Question answer, chapter 1, sections 1 and 2. Hit me. No, but I can probably do 23 or 25. Let's take a look. From which section? Let's see. This one? Verify the family is a solution? 24. All right, so you want to do 23 or 25? Okay. So 25 says verify that second derivative minus 4 times the first derivative plus 4 times the original function equals 0. And the functions in question look like c1 e to the 2x plus c2 x e to the 2x. Okay. So it says verify that these form a solution. And let's assume an appropriate interval. So, 2 different pieces here. Check that it works. What's the interval? Just looking at the functions themselves, where are those functions defined? C1 and C2 are constants. So where is that function y defined? Everywhere except? Everywhere. That one's defined everywhere. E to some number x, that's defined everywhere. X is defined everywhere, and I multiply it by the e to the 2x. Yeah, those are defined everywhere. Perfect. So I can say, oh, this is going to work everywhere. If it works at all, it's going to work everywhere. How do I know whether or not it works? I need the first derivative and I need the second derivative. Now I'll take those and I'll plug them back into that. See if I get 0. So this is y. What's the derivative? The derivative of e to the 2x is 2. Chain rule. And that constant in front stays there. But now, what do I do with that part? Yeah, I got to do the chain rule for the e to the 2x, but what about that extra x? Product rule and chain rule together. C2 times derivative of x is 1. Leave the e to the 2x alone. Leave the x alone. The derivative of e to the 2x is 2e to the 2x. Now, I can gather some like terms here. This is the only piece that's got an x in it. So I have 2c1 plus c2 e to the 2x. That's these two pieces put together. And c2, 2x e to the 2x. But that's just the first derivative. That thing over there says I need the second derivative. So let's do it again. Okay, number times e to the 2x. Same derivative as before, I get an extra 2 out front. And now I got to do the product rule again. I took the constant out front already. So I have derivative of x is 1, e to the 2x, then leave the x, derivative of e to the 2x is 2, e to the 2x. Again, there's only one part that has an x. So I can take this part and kind of combine it with that part over there. So I've got 4c1, 2 and 2 more, that's 4c2 C2 e to the 2x, and then 2C2x. Oh, there's another 2, make that a 4 instead, e to the 2x. Whew. Well, that sucked. Now, one of these minus 4 of those plus 4 of those. 1 second derivative minus 4 first derivatives plus 4 of the original function. One of these minus 4 of these. Plus 4 of the original. The original's all the way back up here. Really, I only have 2 types of pieces here. I have the pieces with x e to the 2x, and then I have the pieces without the x, right? So let's count up how many we got. If I just look at the e to the 2x pieces, I got 4c1 plus 4c2. Then I've got minus 8c1 minus 4c2, and then minus plus 4c1, right? Now with the x e to the 2x parts, I got 4c2 from up there. I got minus 8c2 from here. And then I've got plus 4c2 from there. Wait a minute. What's the coefficient here? What's that add up to? Minus plus 4c1 plus 4c1 minus 8c1 plus 4c2 they both add up to 0. It worked. This is a solution to the differential equation we started with, and we know that solution is defined everywhere.
Maybe actually don't, I didn't know.
You didn't know?
I didn't.
Oh, okay. So the interval comes from looking at the function. So in 24, what's the function? Let's just look at that part. Y equals 2x squared minus 1 plus c1 e to the minus 2x squared. So I'm going to ask the same question I asked. Where is this defined? Is there any place where this is undefined? Polynomial, it's an exponential, defined everywhere. My interval should be everywhere. This was the very last thing we talked about yesterday. Start with the domain of definition of the function in terms of algebra. Where is this defined? And then you say, were there any places where our differential equation gave me problems? In this case, number times derivative, number times derivative, number times function. There's no problems there. Not dividing by anything, no roots, no screwy things there. Run with it. If I had initial values, which none of these do, I'd then say, well, where's my initial value? Which piece of it's in there? We go from the domain to a general set of intervals to the one interval we want. Better? More questions? Talk to me. Yes, ma'am. 1.2, number 18. Um, 17 or 19, pick one. X dy dx equals y. So the first thing I'm going to do is I'm going to ask you to rewrite this equation. Because I think our definition requires us to write the highest derivative alone, that normal form, right? So in this case, I want to get y prime all alone, which makes this into that. Now, we're asking a region of the xy plane for which this would have a unique solution. So that's that big monster theorem, right? I need something to be continuous. I need a rectangle, all that jazz. So I want to think about that formula, that theorem. And that theorem is on page existence and uniqueness, page 17, all the way at the bottom, was one of the things we did yesterday. So I need to think of this function as f of xy. And now I'm going to ask where this function is defined and continuous, and where its partial with respect to y is defined and continuous. Let's just start with this function. Where is this function messed up? When x equals 0. So really, as long as I'm away from the y-axis, I'm okay. Yes? There's no restriction on y at the moment, yes? Okay. Then the other thing I need to look at is partial of f with respect to y. What's my derivative? Which really gives me the same place where that's messed up, right? The only place that's messed up is where x is 0. So, according to the statement of my theorem on page 17, a rectangular region of the plane where both these are continuous is an acceptable region. So I can really define two different regions, either to the left of the y-axis or to the right of the y-axis. There are two possible rectangles here. Rectangle 1 on this side and rectangle 2 on this side. If you pick an initial condition point away from the y-axis, that will work. You're still looking like I slapped you with a fish. Talk to me, Mia. You don't have to duck. No, I'm good.
18, have an xy in the problem.
Okay.
So, okay, find the region 5 like using two variables?
Yes, I'm describing a region in the XY plane. I should describe it with two variables. So what is the, well, I think about it just in terms of the picture. What is the region you're trying to describe? No, in that problem.
X times Y has to be greater than 0.
And where is that? That's either up here or down here. Yes? Now, when I'm taking a square root, I'm allowed to use 0, yes? So I could actually include the edges for just looking at f. When I go to take the derivative, there's going to be some weirdness, and maybe I'll lose some of those spots. But I can start with, yeah, you can be in this place, which is x is greater than 0 and y is greater than 0. You can be in this place where x is less than 0 and y is less than 0. It's a perfectly acceptable description. Yes, Cody.
Why didn't you just write negative infinity 0? Like, why'd you put the X?
Because in the statement of the problem, it says, give me a rectangle from A to B and C to D. So I need to know what's the X range, what's the Y range. X range, Y range, X range, Y range. Now I'm being pedantic by writing that. You could say to the left of the X axis, to the right, sorry, left of the Y axis, right of the Y axis. When I look at the theorem on page 17 and I see this particular way of writing this thing. So that's where I go back and I say, well, in Calc 3, we wrote them like this. So I might as well write it like that again. That was our Fubini theorem version of writing that. Remember that when we did the double integrals? You know, like a long time ago, I wiped that out of my brain. More. Yes.
Yeah.
In which section? This one.
We're just like, okay, I think that, it sounds great, but for, like, I plugged in for the first part, and I don't know, I kind of fits it. But I also think I know what it, like, it's, so basically, with the cosine of, like, whenever you get to the point of the square, like, yeah, about like, whenever I plug in for, y, like, x is the square root of 2. Like, yeah, for the first part, it keeps giving me like I'm not sure how to do like that.
So what I want to do is I want to put that root 2 over here. But then I got to put this pi over 4 in for the t value.
Right. And then I got it. Like, 1 at the same time.
Well, what's cosine of pi over 4? That's root 2 over 2, right? Okay. I don't know how you get, I don't know how you get that both of those are 1 at the same time. Because I've only got one equation with 2 variables.
Yeah, I was being like really right there.
You're going to have to create another equation
Yeah,
for this one, whatever this number is, and then take the derivatives because that's x prime, plug in, you'll then be able to solve for
as I
C1.
was as I was asking that question, like when I kept fumbling, I was like, oh, I need this. No, like I let this.
Yep.
Yeah.
Sometimes asking the question is enough for you to go, I see it. I love those because that means you have answered your own question. That's great. That's the opposite of dumb, Jack. Opposite of dumb. Yes, ma'am.
For me, like, they give us the equation x double prime plus x equals 0.
Wait, for section 1?
Yeah,
Wait, section 2. Oh, yeah, yeah. The solution is x double prime plus x equals 0. Yes. No, you don't have to. What they've told me is that this is a solution to that differential equation. I'm going to believe them. Now, I could check if you wanted to, like we did with Jalen's problem, but I'm going to believe them. They told me this solves the second derivative is equal to the original function. The negative of the original function. Wait a minute, that makes sense. What's the second derivative cosine?
What's the second?
Second derivative of cosine. Negative cosine. Second derivative sine.
Negative sine.
Sine, cosine, minus sine. So if I add sine and minus sine, I get 0. If I add cosine and minus cosine, I get 0. Yeah, that should solve, that should work for the second derivative plus the original is 0. See, the advantage here is I didn't have to do the work to show that that was the solution. I just say, oh, you told me it's the solution? I believe you. We will eventually figure out how to do that work. We just don't have to do it right now. Watch us.
Three at 1.2.
3 on 1.2. So I'm really happy to say that this is another case where I don't have to solve the differential equation. They've given me the solution. And now they're asking me to find the interval for a particular solution. And the solution is y of 2 is 1/3, right, Jalen? That's number 3? Okay. So what I really need to do is I need to figure out what C is. So let me take this information and put it in here. What C value works? Okay, so that means that the correct equation to go through this is y of x equals 1 over x squared minus 1. With me so far? I'm going to ask you the same question I asked earlier. Where is this function undefined? Or, right. So I know my interval is either negative infinity to negative 1, or negative 1 to 1, or 1 to infinity. That's the domain of my function. And the place where this is a solution is one of these three. But now I have an initial condition where which of the three intervals contains the point that we started with? Wow, the point we started with has what x value?
Oh,
The x value is 2. These are x's. X equals 2 is in here. So the appropriate interval for this solution is from 1 to infinity. Homework. Here's the graph of our curve. 1 over x squared minus 1. Well, notice that if I hit x equals 2, y is a third, I'm over here. I have to avoid the places where this function is undefined. So I can keep going to the right, but I can only go back to the left until I get to 1. So that's the only interval I can be sure this works. Makes sense? I love the pictures on this. That helps, I think. But that's me. I'm a very visual person. More questions?
Like, the answer, it's like, written. Like, do we just? Or,
Oh, I was just saying, I'm looking at 1.2. I'm trying to be convenient for you. For 36 and 40,
yeah,
find values of m.
42.
Oh, 42.
Like, yeah, I don't know, I just, like, I think like.
Well, once you know what the values of m are, you say, well, m equals and m equals, but you have to show me how you came up with that.
Like, right now, I don't know.
You're welcome to write me in English or geek speak or math or whatever you'd like, but
Okay.
I need some justification. If you tell me that the answer for number 38 is, I don't know, like 7 and 3, I want to know how you got those.
Okay.
So show me some algebra rationale that you came up with.
Yeah, I was just wondering.
There's no formal paragraph proof thing you need to write. No, this is not discrete. Or abstract. We're going to do a lot of more general results similar to finding these values of m, and then going forward with that for more generalized methods of solving. but that's later in chapter 3. This is a taste of what is to come.
Are we able to set up the problem? Like ask you to help us, please set it up.
Talk to me.
Can you help me with 18 on 1.1?
18. So this says, show that this is a solution by considering it as a function with both looking at the domain and then thinking about the way we solve, right? This is very similar to what we were just doing with the x squared minus 1 thing. So 5 tangent 5x, the trig one?
Yes.
Okay. So let's start with just that statement. What's the domain of this function? Where is it undefined? If I were to graph it on my calculator, where would I see holes, jumps, gaps, asymptotes, any of that?
Somewhere on the y-axis. It's not be higher.
Oh, wait a minute. This is a tangent graph. What's graph tangent look like? Trig was a long time ago.
Maybe like. Maybe it was stuff like,
We do the math dance, right? X squared, absolute value tangent. Yeah, we can do all of it. Right, it looks like this. And there's an asymptote over here and an asymptote over here. If I'm looking at the regular graph of tangent, I know where those asymptotes are. If you don't remember, you go back to the back of the calc book where the trig illustrations are, and I know they're there. But then this, I multiply by 5. I multiply by 5 inside a function. What does it do to the graph? Squeezes them. So they'll get smaller by a factor of 5. I now know where the asymptotes are. Those are the places where it's undefined, which means it's defined in all of the other places, like this, right? We'll be able to make a list. And then it says, that's considering it just as a function. Now, as a solution to our differential equation, if we had an initial value, we would only be able to get one interval. So if you have lots of different choices, then in part B, you're like, oh, just pick one.
Yeah.
That's it. So all you have to do is tell me what the domain of this function is. And then, oh, so as an example, I might be using this interval.
yeah, probably. I'll put the undefined and everywhere it's like 5 and 2.
When we start, yeah. This is where you all should be getting together and talking about these things together, coming to my office hours, but it's not. I mean, is this written clear enough? I think that's a great discussion. It's not what we should have right here, right now. Make sense? Yeah, there are a lot of asymptotes on tangent. It's because it's repeating so often, right? And then we squeeze it so we get them more often. Yeah. More
So
questions?
how was that? Is defined technically everywhere except those asymptotes, so.
Okay, so I would say, just like I did here, I could say there are a whole bunch of intervals, yes? I want to, the first one should list them all, right? You should write the big general. But for the answer to the second part, where it says give at least one interval, then just give one of them. Pick one interval and say, okay, so between these two asymptotes, that works. Because really what you're doing is you're going, it's messed up here and here and here and here and here and here. It's continuous everywhere in between, right? So here's one interval that I could use. Talk to me more. What more questions do you have? Here that hurt.
That's another one.
Yeah.
We do a problem like number 22 on, for section 1.2.
Like 22.
Yeah.
Determine a region in which we have a, wait, didn't we do 19? And then in the same box?
Is that similar?
Yeah, it wasn't, because you were asking about the square root one, which is 18, and we did 19. That was this one. Yeah, 22 follows the same idea.
Just go down the list.
Yeah.
Do 30 then?
30. Verify that we have a solution. Okay, wait a minute. How do I verify something as a solution? Take the derivative and start plugging and chugging. So the first thing we're looking at is that tangent function. What's derivative tangent?
Secant squared.
And then I got the chain rule because there's a square and there's an x plus c inside there, right? But the derivative of the inside is just 1, so that made my life easy. Then show that that satisfies y prime equals 1 plus y squared. Oh, wait a minute. What's 1 plus secant squared? Sorry, what's 1 plus tangent squared? Which is the derivative, isn't it? Y prime equals 1 plus y squared. Yes. So you just showed that it works. And then we go, hey, wait a minute. This is continuous. Now here's a starting point. Here's 0, 0. Part B says the point in question is 0, 0. Tell me why the solution is not defined there. From -2 to 2. Where are the asymptotes of tangent? -2 versus 2. Don't those go past the asymptotes? We're not allowed to cross those. If we're at 0, we can only go as far to the left as -pi/2, no, as far to the right as +pi/2. You wanted to go to -2. You went too far. You crossed one of the forbidden points. Don't do that. That's why we put the dotted lines on the damn graphs when we do those asymptotes. You can't cross here. This is the line of death. Do not cross. Part C says determine the largest interval we can use. If I'm using 0, 0, how far can I go?
Not too far.
But I know exactly how far I'm going. Go to the asymptotes. Now I just need to know where the asymptotes are. Calc 2. I know I'm stretching. We did interval of convergence and radius of convergence for power series. And y'all wanted to shoot you in the head with a bazooka. But when we did that radius of convergence, what we said is we said, well, you can go up to this far and then something breaks. We're doing the same thing here. We're going as far as we can before something breaks. The thing that breaks is that we hit an asymptote in our definition of our functions somewhere. If you go down to the first floor of Lynch, right before you get to Lynch 106, there's a poster on the wall that I'm exploring exactly this problem with power series, where the asymptote is and what's making problems there. It's one of the research problems that I've been barely paying attention to for a while, but I should be doing more of. So I know that there's something interesting that happens when you run into asymptotes. What is it, and why does it work in some cases and not others? So these are actually important, bigger ideas, especially in engineering and calculus. But that's me wandering off topic. Asymptotes are really cool about these things. More questions? I don't have a reason to nail you all to your chairs. You do know that, right? So when you run out of questions, we can just pick this up tomorrow in my office hours. If you got questions, I'll be over in the Enrichment Center from 9:30 to 11:30 and from 2 to 3:30. I think that's what the hours are. Yeah. 2 to 3. So class, 2:20 to 3:35, so 75 minutes in the afternoon plus the 2 hours in the morning. Otherwise, I'll see you all on Friday, where this stuff will be due, so. Got questions? Good. We push to stop recording.